Alright, welcome to Module 2 of World Regional Geography, which is Physical Geography. The significance of physical geography to world regional geography is both complicated and straightforward. So it's straightforward in the sense that physical geography helps us understand the Earth and the processes that have shaped the Earth. But in terms of thinking about how world regions are formed, what we'll be exploring for the rest of the semester is how we both affect and are affected by the Earth system. So how humans and humanity have shaped the Earth and vice versa. Therefore, physical geography is a good starting point when it comes to understanding the world regions. Alright, so what is physical geography? Basically, it is a discipline that addresses Earth's natural processes and their outcomes. There's a couple of different ways of looking at this. So there's the side that emphasizes the physical, and there's the side that emphasizes the physical and human relations. So earth science is what you might call an allied discipline, whose focus is basically the Earth itself, how the Earth is formed and how it functions. The scale of earth science is often very large and geologic. I mean that both in terms of time and space, right? So we can talk about geological time periods, the Jurassic, the Cretaceous. So the focus of earth science, generally speaking, is not on humans. Physical geography, on the other hand, looks at processes of interaction between natural and social phenomena. The spatial, meaning in space, and temporal, meaning in time, scale can vary from extremely localized up to global, incorporating the entire Earth system. Landforms, weather, and natural disasters are popular topics in physical geography. And this is because these are the phenomena that are shaped by a combination of human activities and natural forces. So for instance, humans have shaped the flow of rivers, the formation of landscapes, we've transformed coastlines, and we've certainly changed the weather and the climate. And in this way, humans have contributed to the formation of world regions as they're classified today, changing the physical landscape into something new. Alright, to give you an idea of the kind of work that physical geographers are doing here at Ohio State, let's pay a digital visit to the Byrd Polar and Climate Research Center, which if you want, you can also visit physically. They're located just over on West Campus, and they do give public tours. So I mentioned that physical geography tends to look, on one hand, at the Earth system on a broad geological spatiotemporal scale, and on the other hand can also look more closely at a finer spatiotemporal scale at Earth system-human interactions. So over at Byrd, they have quite a few different research groups looking at different aspects of the cryosphere of our planet. In other words, where is there stuff that's frozen? And these research groups span those two aspects of physical geography that I described. Let's look more closely at two of them, not just because they're my favorites and run by great people, but because they embody these two different aspects of physical geography. So here we've got the Ice Core Paleoclimatology Research Group. This is headed by Dr. Ellen Mosley Thompson and Dr. Lonnie Thompson, who are foundational giants in their field. Basically, their research involves drilling ice cores from all around the world in order to generate data about the state of the Earth system going back millennia or even millions of years. So of course, nowadays we take current measurements of temperature and the concentrations of different elements in our atmosphere, but unfortunately no one was doing that for us 5,000, 6,000, or even a few million years ago. However, by looking at ice cores, they're able to piece that information back together and tell us really important things about the history of our Earth's climate, which couldn't be more relevant now that we're undergoing climate change. On a somewhat finer spatiotemporal scale, we have a group like the Glacier Environmental Change Group headed by Dr. Brian Mark. They look at coupled human physical systems in glacial regions. An example of this would be in the Andes, where human societies rely in large part on runoff from melting glaciers, seasonal runoff from melting glaciers, for their water supply. Now, as glaciers are receding year to year, those societies need to be able to predict how much water they'll have in the future. So this is a very practical, very current application of physical geography that's looking at a much finer time scale, spanning seasons and years rather than centuries and millennia. Alright, a quick introduction to the Earth system and the forces that are acting upon it and within it. So probably paramount to our lives is the solar energy that we get from the sun. And this arrives in the Earth system through a particular kind of process, which we'll go into more detail on in the next slide. In addition to energy that we're getting from the sun, the solar energy, we do have internal energy, heat coming from within, coming from our core. And this drives the plate tectonics that cause geological events, such as earthquakes, which can sometimes lead to tsunamis, volcanoes, and then in the longer term, the very formation of the continents, canyons and mountain ranges, and the other geological features we have on the surface of the Earth. In addition to the fluid dynamics of the magma driving plate tectonics, we have the fluid dynamics of the atmosphere and the ocean, which are circulating in certain kinds of currents all year round. And yes, the atmosphere is of course also a fluid and subject to fluid dynamics. So I mentioned that we're getting the solar energy in a particular way. Now you've probably heard of this before, but in case you haven't, or if you haven't heard of it before, you've experienced it if you've ever sat in a hot car on a sunny day. But basically, what's going on with the greenhouse effect is that our atmosphere, be thankful that the ozone is there, protecting us from cancer and being cooked alive. The atmosphere reflects some solar energy back into outer space, but much of it gets all the way to the surface of the Earth, where it heats the surface, and then that heat energy is trapped within our atmosphere, which is, again, a very good thing. Otherwise, we would look a lot like Mars. But when this gets carried away, when there's too many greenhouse gases, too many gases that are trapping that solar energy, that heat that hits the surface in our atmosphere, things go badly. An extreme version in our own solar system would be Venus, right? Venus is just a giant ball of what we would consider terrible weather because of the greenhouse effect gone to the extreme. And in fact, some of the earliest research on climate change was done by planetary scientists who were looking at Venus as an example. And the greenhouse effect is one of the things that is driving climate change. The main greenhouse gas that you're most familiar with being carbon dioxide, which has been increasing its concentration in the atmosphere. But there are also other major greenhouse gases. Alright, so this diagram gives you an idea, a visualization as if we were in outer space looking in, which I've never done before and probably you haven't either, so this will be helpful, showing the Earth's seasonal rotation around the Sun. So I'll pause here in April. As we can see, wow, spinning quite quickly. Here we are in the northern hemisphere. These two green lines are at 23.5 degrees north and 23.5 degrees south. The Tropic of Cancer in the north and the Tropic of Capricorn in the south. And the area between them, which many of you will want to visit or have visited on spring break, is called the tropics. What makes the tropics is the fact that at all times of the year, this is where the sun is most focused. Up here, we can see the Arctic Circle. Alright, so you can see right here in late June, this is when we have our summer solstice. Oh, there we go. Okay, so this is when, for us, the days are longest because the sun, the Earth is tilted such that the sun is at its northernmost. This is why it's summer for us, because basically in the northern hemisphere, we're tilted toward the sun. As the Earth continues to rotate on its axis, we in the northern hemisphere will get cold and snow. And at this point, come on, Earth, cooperate. At this point, it will be hitting the equator. But then, when it's summer in the southern hemisphere, it will be hitting down here at noon. Alright, this diagram gives you an idea of some of the prevailing atmospheric circulation. Now remember that both the atmosphere and the ocean are circulating in ways that are subject to fluid dynamics. So probably some of the most important aspects of atmospheric circulation are to think of these Hadley cells. So again, there's one in the northern hemisphere and one in the southern hemisphere. And you can see that they're taking place in the tropics, where the sun is most concentrated throughout the year. And this is driving a lot of the atmospheric circulation that we have around the world. You'll remember last winter when we had the so-called polar vortex. Now, to oversimplify things, that occurred when you can see these polar winds we have up here. These winds that are usually driving weather across North America, if you've ever watched your local weather station, you've probably seen the storm fronts progressing from west to east. And here in Columbus, we get plenty of those, so we know what the weather is because it is whatever it was in Chicago yesterday. The temperature difference between this mass of air and this mass of air, which is usually a lot because this is really, really cold, wasn't as much as it usually was. And so this mass of polar air was able to get further south than it's supposed to, which is why you were all able to do that slightly dangerous trick with the boiling water and throwing it out. Anyhow, hopefully we won't get that again this weekend, but this is what drives it. It's the planetary atmospheric circulation. This demonstrates the ocean circulation. So here we see the warm shallow current and the deeper colder currents circulating throughout the planet. And of course, this interacts a great deal with the atmospheric circulation. And the atmospheric circulation and the ocean circulation are what drive a lot of our weather. So, for instance, you might have heard in the news that soon it's time for another El Nino cycle. That has to do with the shifts with these circulations, and it changes the weather in our part of the world. And here's another view of the ocean circulation. You've probably heard of the Gulf Stream. So back before there were engines on boats, this was incredibly important to sea navigators. And if you've been following at all the disappearance of MH370, then you'll remember hearing about the currents that brought debris from the probable crash site around here, kind of west of Australia, to Reunion Island around here, right? And so by modeling those currents, they were able to do probability models and say, here's a place where the debris could have plausibly entered the ocean X number of months ago. It's because we have a pretty good grasp on how water circulates through our oceans. And then finally, much as the fluid dynamics are acting on the atmosphere and on the water in the oceans, they are also acting on, in some ways, the continental plates that we live on top of and the molten material beneath them. So basically, the 12 large plates floating on this molten material are constantly in movement. Now, by constant movement, that means a constant pace of geologic movement. It's moving on geologic time. To the extent that we notice it in our own lifetimes, it's because there might be an earthquake or a volcanic eruption or a tsunami. But in order to actually see the continents take on a drastically different shape, you would have to live for a very long time, a few million years. But geomorphology is where we get the surface of the Earth that we know as we do. This gives you an idea of basic types of landforms, right? And mountain ranges and valleys are formed by the plates either pulling apart or colliding with one another. So all of these varied and beautiful features of the Earth's surface are being driven by a combination of plate tectonics and then atmospheric and ocean currents that are depositing materials in some places, eroding them from other places, right? So there's erosion caused by wind, erosion caused by water, and it's doing more than making really nice places to hike. It's shaping the surface of the planet. These plate boundaries show basically where the plates are colliding with each other, where they're pulling apart, and where they're pushing into each other, sometimes in a way where usually one goes under and one goes over, right? That's called subduction. And when there's a little bit of extra pressure, that's what's causing earthquakes. Here's a more detailed diagram showing exactly how that happens. So a divergent plate boundary, here the plates are pulling apart. Whoops, the plates are pulling apart. That's marked by this kind of, you can see from the key, this kind of line. The subduction zones are when they're pushing together, and one is going under the other one, as opposed to a transformational one where they're kind of, imagine two trains kind of passing by one another, except in this case they're also rubbing up against one another. Now, the Himalayas are a special case. I hope you get a chance to visit if you haven't. They are very beautiful. I spent some time right around here in northern India, and I've also been on the other side of the border. It's an incredibly beautiful region, and it's a gift of geomorphology. The Eurasian plate and the Indian plate are of a similar density. So instead of normal subduction with one going under the other as they're crashing into each other, which they've been doing for a very, very long time, they've created this amazing and high geological feature, the Tibetan Plateau and the Himalayas. All right, let's turn our attention to climate. So, first of all, the Himalayas are a great place to think about climate because the polar regions, including, well, the polar regions north and south, and also the rest of the cryosphere. Remember, cryosphere being a fancy way of saying the places where there's lots of frozen water, are experiencing climate change faster than other parts of the world. And this has to do with atmospheric dynamics and temperature dynamics, which we could go into more detail about later, but for now it's sufficient to understand that those regions are a useful bellwether showing that climate change is here and happening quickly. So one thing that we have to understand before we talk about the climate is that there's the difference between weather and the climate. Having a particularly cold winter doesn't mean that there's not an overall warming trend, or vice versa. So weather is kind of the day-to-day, whereas climate is the prevailing overall trends. Now, there are different types of climate, which create different types of landscape. These are driven in part by geologic features, right? So I'm sure that back in high school you learned about mountain ranges and clouds and deserts, and are also driven by the relative position of a region on the planet. So tropical, remember, means that it's between the Tropic of Cancer and the Tropic of Capricorn. So in terms of latitude, between 23.5 degrees north, 23.5 degrees south. A temperate climate is where we live, in between the tropical and the polar. The polar is inside of those Arctic circles. Now, we have precipitation relatively year-round in Ohio, which is very nice. Although some people may not think so when we're talking about snow and it's March. But in other parts of the world, there's a seasonal monsoon, which arrives at a certain time based on a complicated interplay, possibly. So, for instance, the Indian monsoon is driven by an interplay between the ocean currents, the water temperature of the Indian Ocean, and then the temperature on the Tibetan Plateau. So this temperature, the temperature differential, the way it interacts in a certain way at certain times of the year, is what brings water, or what drives the monsoon that brings water to everyone who's living in this whole part of the world. Okay, again, weather and climate, not the same. Weather describes the current atmospheric conditions in a particular place at a particular time. Climate is the longer-term trend. And these regions will, of course, change as the Earth's climate is changing. But here's a snapshot now of different climate regions. So you can see that we're at what's called, we're in a continental mid-latitude type of region here in Columbus. Now, water and land absorb heat in different ways, and of course, give that heat to the atmosphere in different ways. So they're collecting it and re-radiating it, driving weather in different ways. Here in Ohio, this is the type of climate that we have, being driven mostly by the way land is absorbing and re-radiating solar energy. So we have hot summers and cold winters. Now, a maritime climate, because it's driven in large part by the presence of the ocean, has a different kind of seasonality. Climates with cool and cloudy summers and cold winters, but without sub-freezing temperatures. And again, this is because of the mediating effect of the ocean. Climate change refers to a change in climatic conditions over time. And this is happening, of course, in terms of average temperature at a global scale, but on a localized level is having, in some places, much stronger effects, much more noticeable effects. As I mentioned, especially in the Earth's cryosphere, which is bad news for us. Now, there's a 97% scientific consensus that human activity is causing the climate to change. So mostly this is referring to the burning of fossil fuels, oil, natural gas, coal, but can also be caused by other sources of human emissions, like land use change. For instance, a forest captures a lot of carbon, while a beef farm, if the forest is clear-cut, emits a lot of greenhouse gases. So this is the famous Keeling curve, which shows this is an amazing, although for us it should also be a sobering record of the concentration of carbon dioxide in the atmosphere, taken at the Astronomical Observatory in Hawaii, going back to before 1960. And what we see here is the seasonal variation. This is because most of the landmass, and therefore most of the forests, are in the northern hemisphere. And remember, if you think back to the Earth tilting on its tilting on its axis as it's rotating around the sun. If most of the forests, if most of the biomass is experiencing summer at the same time, then it will be storing carbon, and therefore the level will fall during summer. Anyhow, that's why it's a zigzag, but it's been steadily increasing, and currently we're over 400 parts per million. So you've probably heard of 350.org. 350 being an approximation of maybe what could be a safe amount of carbon to have in the atmosphere to avoid a drastic temperature change over the next century. In any event, we're nowhere close to it. We're much higher than we need to be. And so this is the most reliable and most recent record that we have of carbon dioxide concentration in the atmosphere. But think back to Ellen and Lonnie Mosley Thompson and other physical geographers here at Ohio State and around the world drilling those ice cores. So that is how we have a paleoclimate record. In other words, a record of the probable carbon dioxide concentrations in the atmosphere going back much further than before we were measuring it with our modern instruments. So we can extrapolate using those ice cores and other means, rings of trees, sediment deposits in lake, and establish across all of those different methods a very, very, very accurate, a good guess of what the climate was doing before we were taking these measurements. And we can see around us the real world effects of a warming world. So I mentioned that the cryosphere is experiencing change particularly quickly. So you've probably heard about the receding snow cap on Kilimanjaro, melting glaciers in Greenland, summer melt in the North Pole getting crazier and crazier every year, decrease in snow cover, tree lines shifting poleward and upward, so meaning going to higher elevation and also further north, spring coming earlier, species migrating north and south and again to higher elevation because the temperature that they're adapted to, the location where it's that temperature, is moving closer to the poles and at higher elevation. As sea ice decreases and as ice sheets and summer ice cover, for instance, at the North Pole, melt, the sea level of course rises. The ocean, which has been doing a good job to this point of absorbing all of this excess heat, although it's leading to ocean acidification, its temperature will continue to rise. And as the ocean gets overwhelmed as the heat sink, the atmosphere will experience that faster and faster. So these are just a few of the very observable effects of a warming world that we've been experiencing and will continue to experience as the century moves on. And again, with the decreasing glaciers and snow cover, think back to the Tibetan Plateau and all of those rivers that originate on it. These rivers are fed by glaciers, and something like 25% of the Earth's population lives somewhere in the basins of these rivers, meaning they're relying to some extent, in some cases exclusively, on these rivers for water. So as glaciers are melting, as it's changing the amount of water being discharged into the rivers seasonally, and possibly in some places in the summer not discharging far less or not discharging anything at all if the glacier is gone, it's not just taking away, the pretty glacier is gone, when we go hiking it will be brown instead of white. It's drastically changing the way that vast numbers of humans are going to have access to water. Now, this is all part of something that some scientists, some geologists, have started calling the Anthropocene. Back in secondary school, you may have learned that we're in the geological age of the Holocene, the past 10,000 years since the last ice age. The idea of the Anthropocene posits that human activity, now exactly which element of human activity is up for debate. Is this due mostly to combustion? Is this mostly about land use change? Is it a combination of all sorts of different factors? But basically, the idea is that human activity has changed the Earth system so much that we can no longer say that we're in the same geologic era that we were before. We can no longer say that we're in the Holocene. So now I'm sure you know the prefix anthro, meaning anthropology, the study of humans, so Anthropocene, meaning literally the human era. All right, and what does the human era look like? Certainly a huge part of this is climate change, which again, it's important to remember that this is having both localized and globalized effects in different places. So on one hand, we have large-scale and singular events like storms that are strengthened by climate change, droughts that are worsened by climate change, loss of ecosystem, which leads to a loss of biodiversity. Because remember, if animals are migrating towards the poles and to higher elevations, then organisms that already live near the poles or already live at higher elevations eventually will have nowhere to migrate to. So there are some localized effects, but then there are also more global level effects, such as sea level rise and increase of average temperature. And this is what the Intergovernmental Panel on Climate Change, the IPCC report, estimates the next century will look like in terms of the most conservative, or one might call it the most optimistic model, or the most pessimistic model. Reality probably, of course, ending up somewhere in here. And these are the projections for sea level rise. So what's already happened, and as demonstrated from instruments, estimates based again on the same kinds of paleoclimate work that I discussed earlier, and then projections of what will be going on in this century. Ocean acidification. Another way of thinking about the Anthropocene and the human impact on the planet is in terms of land use change. This human footprint index map shows the extent to which human activities have changed the surface of the planet. Now, part of this includes settlement, so building cities, which are denoted by these colors, and you can see Cleveland up here, here's Columbus. You can also see that crops have had a huge impact, especially on our continent, in displacing what previously was grassland or forests. Or another way of thinking about this is looking at the footprint, for instance, of Washington, D.C. and Baltimore between the mid-19th century and the end of the 20th century. Another way to visualize this is with a really cool tool that you can access here on Google's Earth Engine, which is making a time lapse of satellite imagery from the Landsat and showing land use change over time. There are some very dramatic examples of this. And what's great about this website is that you'll be able to zoom in on a particular area that you're interested in seeing. So you can zoom in on your hometown, or you can zoom in somewhere you've been on vacation, a landscape that you're familiar with, and see the change over time from space. Okay, so here's a relatively short period showing Las Vegas's growth over time. Now take careful note, not just of the huge amount of built-up area that appears relatively speaking, very quickly. But look at the green that comes along with it. And ask yourself, if it was desert before, where's the water coming from to irrigate these lawns and these golf courses? Meanwhile, in Dubai, you can see a dramatic change from practically empty desert to built up urban area. Thank you for watching. I hope that this lecture has been a helpful introduction to some of the basic major elements of both the Earth system and thinking about how humans and the Earth system interact. Make sure that you do the reading in the textbook and check the Module 2 schedule to make sure that you're keeping up on all of the assignments, and remember to get your assignments in by the deadline. So thanks everyone for watching, and I'll see you guys next week.